All right, welcome. Today, we're going to put on our detective hats and dive into a pretty cool mathematical mystery. See, hidden inside a research paper is a secret code, a code that unlocks a really rare and fascinating type of number. So let's get this investigation started. I mean, really think about it. What makes a number special? Is it because it's a prime number or maybe a perfect square? Well, for mathematicians, some numbers are special because they fit into more than one category at the same time. They kind of live at the intersection of different mathematical worlds, and finding them, well, it's like discovering a whole new species. And that brings us to our main suspect, the triangular rectangular number, or TR number for short. Now, these are super rare integers that are, you guessed it, both triangular and rectangular at the exact same time. You can see the first few here, 0, 6, 2, 10, and man, they get big fast. The question is, how do we find all of them? Okay, so here's our game plan. We'll start by looking at this special kind of number. Then we'll break down what triangles and rectangles even are. After that, we'll uncover the master key to finding them, something called Pell's equation. Then we'll see how that gets turned into an algorithm, and finally, we'll find out why making that algorithm super fast is the real breakthrough here. So the mystery is officially afoot. Our goal here isn't just to stumble upon a few of these TR numbers. No, we want to build a rock-solid method for generating every single one of them in perfect order. To find a number that has two different properties, you've got to understand each one on its own first, right? So let's examine the evidence. What exactly makes a number triangular and what makes it rectangular? Okay, first up, triangular numbers. Mathematically, these are numbers you get from the formula n times n plus 1 divided by 2. That gives us this sequence starting with 0, 1, 3, 6, 10, and it just keeps going. But what does that actually look like? Well, just picture a set of bowling pins. You've got 1 in the top row, 2 in the next, then 3, then 4. Add all those pins up, and you get 10. It forms a perfect triangle. So the number 10 is a triangular number. It's simple, it's visual, and it's kind of elegant. Now, for the other half of our puzzle, rectangular numbers. These are actually a little more straightforward. They're just what you get when you multiply two consecutive numbers together. So 1 times 2 is 2, 2 times 3 is 6, 3 times 4 is 12, and on and on. But wait a second. Did you notice something? The number 6 just showed up in both lists. That's our first non-zero TR number. And to visualize this, just think of a grid. The number 12 can be perfectly laid out as a 3 by 4 rectangle. That's why it's a rectangular number. So our mission, really, is to find the numbers that can be arranged as both a perfect triangle and a perfect rectangle. Okay, so we've got our building blocks, but just checking every number one by one to see if it's both triangular and rectangular, that would take literally forever. We need a shortcut, a master key. And it turns out that key is a famous piece of ancient math known as Pell's equation. Now, I know this might look a little intimidating, but the idea behind it is just brilliant. Pell's equation is a special kind of formula where you're only looking for whole number solutions for x and y. The researchers on this paper figured out that if they set up the problem just right, the solutions to a very specific version of this equation would lead them straight to the TR numbers they were hunting for. And this is where the algebra becomes visual. Every single whole number solution to Pell's equation corresponds to one exact point on this curve, which is called a hyperbola. Pell's equation is the tool that lets us find those precise points, and each point holds the secret to generating the next RO number. So we have the theory, this ancient key, but it's the 21st century. We don't solve these by hand anymore. The real work in this paper was translating that beautiful old mathematical theory into something a computer can actually understand and run, an algorithm. So the really crucial part is this. They didn't just find a formula for one TR number. They created a recipe that basically says, if you have the last TR number, here's exactly how you calculate the next one. In the world of math, this kind of step-by-step recipe has a name. It's called a recurrence relation. And this slide just perfectly illustrates what they did. On the left, you've got the mathematical recurrence relation. That's the abstract recipe. And on the right, that's its direct translation into Python 3 code. This is where theory becomes a real practical tool. One is the language of math, the other is the language of computers, but they are saying the exact same thing. So what does that code spit out? This, the first few TR numbers, all generated perfectly by the algorithm. And notice how the values for x and y, which come from solving Pell's equation, are used to get that final TR number. But just look at how fast they grow. From 6 to 210, then bam, over 7,000, then over 120,000. Trying to find these by hand, it would be completely impossible.
So we found them. Case closed, right? Well, not quite. The final, and you could argue the most important part of this investigation isn't just that they found the numbers, but how fast they found them. This is where the story gets really, really interesting. I mean, computers are already blazing fast, right? So who cares if an algorithm is a little bit quicker? Well, in the world of computer science and solving really complex problems, the difference between slow and fast can be the difference between a problem that's solvable and one that's, for all practical purposes, impossible.
A good way to think about it is that there are two kinds of problems. You've got NP problems, which are like a giant, complicated labyrinth. Finding your way through is incredibly hard and could take forever. But if someone just hands you a map, the answer, it's super easy to check if it's correct. Then you have P problems, which are like a straight, open highway. There's a direct, fast path right to the solution. And here it is. This is the punchline, straight from the paper's conclusion. By using that really clever recurrence relation, the researchers took a problem that was like a labyrinth, an NP problem, and they turned it into a highway, a P problem. They found a direct, incredibly efficient route to the solution, which minimized both the time and the computer memory needed to get there. And we're not talking about a small improvement here. Turning an NP problem into a P problem is a massive leap. It's like instead of wandering through a maze for a million years, you can now just drive to the finish line in a couple of minutes. The reduction in the amount of work the computer has to do is just enormous. So what's the big takeaway here? Well, it means faster calculations. It means using less energy and less computing power. It's a really elegant solution to what was a pretty tricky problem. And maybe most importantly, the method they used, this whole idea of using a recurrence relation to cut down complexity, that's a technique that could potentially be applied to solve other tough problems out there. And that leaves us with a pretty fascinating final thought. This whole thing started with just a simple curiosity about numbers that are shaped like both triangles and rectangles, but it ended with a powerful lesson in computational efficiency. It really makes you wonder, doesn't it? What other seemingly impossible problems, in fields from medicine to finance, are just sitting there, waiting for the right mathematical key to turn a labyrinth into a highway?